Here's another example. A certain bacteria is known to double every 4 hours. Write a function that models this growth. If the culture starts with 300 bacteria, how many bacteria will be present after 1 day, or in other words, 24 hours? So we'll start with our exponential growth model. Y is equal to a sub 0 e to the kt. So the function is known to double every 4 hours. And so it doesn't, so let's take a look here. It says it starts with 300 bacteria. So we first need to solve for k. So if it starts with 300 bacteria, we'll use that as our initial amount. If it doubles, we know our final amount is 600. K we don't know, but we know this happens after 4 hours. And so this is our initial model. We'll divide both sides by 300. Now, in the previous examples, I always left this fraction because the fraction was not a friendly fraction. It had a decimal involved. But this comes out to simply be the number 2. So 2 is equal to e to the 4k. Again, we'll take the natural log of each side, allowing us to bring the power down. So the natural log of 2 is equal to 4k times the natural log of e. The natural log of e we know is equal to 1, so we don't need to carry it around with us. We'll divide both sides by 4, and so k is equal to the natural log of 2 divided by 4. So the natural log of 2 divided by 4 is 0.1733. So our model then, our value for k is y is equal to a sub 0 e to the 0.1733 times t. If the culture starts with 400 bacteria, how many bacteria will be present after 1 day, or in other words, 24 hours? So to answer this question, we would simply take y is equal to our starting amount, 300, e to the 0.1733 times, and time in this problem is measured in hours, so t is 24. So this one we just have to enter into our calculator. So we have e to the 0.1733 times 24, and then we'll multiply that by 300, and we come out with an answer of 19,206. Now you may have wondered why it was okay to start off the problem assuming that there were 300 bacteria present. You might have wondered, would it have changed the problem if we had started with a different number of bacteria? Notice if we had started, say, with 10 bacteria, and we want it to double, that means we would have 20 in 4 hours. We would have started this way, 10 doubling into 20. Our first move would have been to divide both sides by 10, and we still would have ended up with this equation, the same equation that we started with over here. And so it doesn't matter what we choose as our starting amount to solve for k. Anything would do, because essentially when you do the division, you'll be solving the same problem. All right, here's one for you to try. I'll get you started, and then we'll see how you do. Okay? So the population of Texas in 2000 was 21 million. In 2010, the population reached 25.2 million and was growing exponentially. Find a function to represent the growth of the population. So why don't you give that a try? Okay, here you go with the solution. So y is equal to a sub 0 e to the kt. Time is going to start in the year 2000, and this is what we started with. So this is our starting amount. In 2010, that's 10 years later, this was our final amount. And so we have this equation, 25.2 is equal to 21 e to the 10k. And we'll solve this as we solved the others by dividing by 21. Taking the natural log of each side, allowing us to bring down the power. So we'll have natural log of 25.2 divided by 21 is equal to 10k natural log of e. We'll divide both sides by 10, and that will give us our value for k. So the natural log of 25.2 divided by 21 divided by 10 gives us a value of k of 0.0182. So our model would be y is equal to our starting amount, 21, e to the 0.0182t.